Okay, so how is it related to our setup here? Now I have drawn the same figure, almost the same figure here on the right, but I have actually added a hemisphere, like an invisible hemisphere around point P. The reason for adding this hemisphere is I want to compute the solid angle that is seen by this surface, by the light source from point P. Now the way to compute a solid angle is you take the object, okay, for which you want to compute a solid angle, and then you project it. You project it along the basically towards your point. Okay, so let's connect this. Let's connect this here. Okay, and once you connect all of these, so you are going to end up with a shape that's here. Okay, so this is basically the solid angle. This part here is the solid angle that is covered by this area light, okay, with respect to point P. Now you can imagine that this light can only send illumination to point P from this area. Okay, so everything that falls into this solid angle. So it cannot really, like, all the rays that reach the light here must pass through this solid angle here, this area. Okay, so this is important because we say that the light that comes from this ray here is L, right? We said this is equal to L. But how many of these do we have? Okay, how many of these rays, or what is the total coverage of these rays? The total coverage is actually the size of this area here. Okay, not the real area of the light source, because you can imagine the light source can be tilted. This light source, this one is like that, but if the light source is tilted like this, you may have even zero solid area. If it is like perfectly parallel to the light direction, the solid area may be almost zero. But if it is facing towards the point, its solid area is going to be larger. So what we must do is we must actually take our L, okay, and we must multiply this by the solid area that is subtended by this light at point P. How can we compute the solid area? Now the solid area there's a relationship like this. The differential solid area is equal to the differential area cos theta. I will write cos theta O because we are projecting along this direction, and this is the normal of the surface. Okay, so we are using this cosine theta divided by the distance square. Okay, so in other words, for this light of of size A, okay, the total solid angle that's subtended by that is going to be something like that. You are going to integrate this, okay, over the surface of the light. Okay, so we are integrating all small differential pieces and how much of that is visible. Okay, so how can we do that? Well,